In this video, I'm going to be investigating a particular optimization problem. I'm looking at what is the height of some square-based box where the volume has a constraint on it. The volume is 100 units cubed, but what our goal is not just any box, but the box that has minimal surface area. So it's the surface area I'm trying to minimize, but subject to the constraint that the volume here is fixed. Okay, so what's the first sort of step in my process for optimization problems? I think it's this. We want to try to draw some picture that represents what on earth is going on. So I'm going to do that, and I'm going to begin by making my square box look something like this. All right, let's see if I can draw. Now, drawing a picture isn't enough. We also want to label this particular diagram, and we want to stick with whatever labels happen to be written down. This is actually quite important. We don't want to just be doing a sort of derivation where we write down any symbol that isn't clearly defined. So I'm going to say that I've got a base down here where the one side length is x, and because it says that it's a square base box, that tells me that the base has to be a square, so it's actually the sort of length and width are both x. And then we've got some height, and I'm going to call the height here y. All right, now let's try to write down a couple different equations. First of all, I'm going to write down my constraining equation, the volume equation, and it says that the volume, which we're told is equal to 100. Now, volume of a box, we know what that is. This is length times width times height, so it's the x times x again, so x squared, all multiplied out by y. Now, I could solve this for either x or y, but notice that in my question, one of the things that it asks for here is it asks for the height of this thing. I'm asking for what the y is. That's what I want to know is my final answer. So I'm going to solve this thing for the x so that I can get rid of the x's in the future. So my x is all written in terms of y. I, of course, could have gone the other way around. I could have solved for y in terms of x, but this question asked for the height, and so that's why I want to get rid of the x. I want to have y's in my answer. All right, so that was the volume formula. Now let's go and try to figure out what the surface area formula is going to be, because that's what I'm going to be interested in next. Now, my surface area, this surface area consists of 6 panels, a bottom and a top. Then there's 2 sides here and another 2 sides there. So let's try to go and figure out what this is. Well, the bottom and the top, what's those areas? So those areas, the bottom is going to be equal to x squared, and the top is exactly the same. So this is going to be just 2x squared. And then, if I want to look at, say, this front panel here, it's going to be x times y. And in fact, all 4 of these panels are exactly the same because it's x and x on the bottom. If it were something else, x and 2x, or x and 7, you'd have different panels. But in this case, because it's x and x, all 4 of the panels are the same. So there's going to be 4 copies of x times y. Indeed, if I try to fill in this front side here, that's going to be a height of y and a base of x. Okay, so that's my surface area formula. And remember, surface area is what I'm trying to minimize. I'm trying to find what height minimizes my surface area. All right. Moving right along. Now what I want to do is I want to go and I want to take this formula from our constraint, this x, and I want to plug it in anywhere where I can see an x. And the reason is I want my surface area only in terms of the thing I'm interested in. I claimed I was interested in the height y, so that's what I'm going to do. If I was interested in the x, I would have said so, and I'd be substituting in y, but I'm interested in the height. Okay, so let's do this. We're going to say that the surface area, in this case, because I asked for it in terms of the y, is therefore equal to 2, x squared is going to be 100 divided by y. And then x is going to be 1 over square root of y times 10. So I think it's going to be 40 times the square root of y on top. Y on the top divided by square root of y leaves square root of y on the top. Okay, this is pretty good. So now I've got this as a function of y. Next step. Differentiate, set it equal to 0. By the way, I'm going to quickly pause just for long enough to note here that the domain of this equation, now I clearly don't have negative y values, it doesn't make sense to have a negative height. You can sort of debate whether you want to imagine a box with, exactly 0 height to it and sort of like infinite base. A bit of a weird thing. I'm going to say that my domain does not include 0, and it's going to be going all the way up to infinity. Indeed, this formula here, the division out by y, it represents this fact that we're not going to really want to be including 0. Maybe you could interpret it in that way if you wished. Okay, moving right along. Now I want to go and I want to differentiate with respect to y and set it equal to 0 to find all of my critical numbers. So, if I take the derivative of my surface area with respect to y, first term, this is going to be minus 200 all divided out by y squared, plus derivative of y to the power of 1/2, which is square root y, is 1/2 divided by square root y, so this is going to be equal to 20 divided by square root of y. And what we're interested is to set this equal to 0. This is how I'm going to go and be able to find my critical numbers. All right, so I have this equation. I'm going to try to simplify it just a little bit to make it easier to solve. First, I'm going to multiply by y squared. This is going to tell me that minus 200 plus, okay, then if I'm multiplying by y squared, but I'm dividing by square root y, dividing by square root y is like y to the 1/2, so y squared divided by y to the 1/2, this is going to be plus 20 y to the 3/2 is equal to 0. Or I can divide out by 20, and I can say that, therefore, minus 10 plus y to the power of 3/2 are equal to 0. Or, in other words, I can say that y is equal to the cube root of 100 squared, or 10 squared, which is 100. All right, so this here is my critical number. It is the value of y where the derivative is equal to 0. But is it a minimum? Is it a maximum? Is one of these ones that goes up and flattens out and carries on? We don't know. We've got a critical number, but we still have to investigate whether it truly is a minimum. So the way we're going to do this is our sort of last and in some ways a very crucial portion, is I'm going to apply the first derivative test. So let's do that, and that's going to verify for me that indeed this thing that I have is going to be a minimum. So how does this work? I'm going to come along here, I'm going to plug on that value, the cube root of 100, there it is, and what I'm interested in is what happens to this surface area derivative to the right of the cube root of 100 and to the left of a cube root of 100. That's what I have to investigate. Well, the equation that I want to look at is this one right up here. I want to imagine that if I was to make y bigger than this, bigger than the cube root of 100, we know that at the cube root of 100 this is equal to 0, but if I came in here and I put in a bigger value, it would become more positive, and therefore this left-hand side would be positive. So it's positive over here, but if I put in smaller values, then this would be a smaller number. The minus 200 would be bigger, and so it would be negative. So in other words, what we have is something which is decreasing and then increasing, so it truly is a minimum. All right, now let's go all the way back up to the original problem and make sure that we've actually solved it. Okay, so what did the original problem tell us? It told us we wanted the height. Good, I was doing height, I was figuring out y. If I'd asked for something else, I would have had to do something else. I was asking for the height, and that's what I did. What is the height of a square base box with volume 100? Well, I input my constraint, the volume equal to 100, and I was minimizing the surface area. And not only did I minimize it and get a critical number, but I verified that it was indeed a minimum. So I am content. I believe we have solved this problem. All right, so just to summarize here, remember that the first step is to draw that picture. We want to carefully label the picture where we respect whatever variables we put inside of our picture. We write down our constraining equation, that was volume in this case. We write out down the thing we're trying to minimize or maximize, that was the surface area. Go ahead and find all of the critical numbers, and then when you found those critical numbers, you have to test, are they minimums or are they maximums? And in this case, it was a minimum.